So, a brief introduction to information theory. So far, basically what have we done? We've sort of built a house on top of probability of error. So we basically said, here's how you calculate probability of error in a single user case. And then we've extended that in all kinds of different ways, and in every case it sort of all come back to the same expression, which is that ERF-C, that one that we just drew. So basically everything that we've done from when we derived that expression until now has been, how can we rearrange this expression so that we can get back to that ERF-C. Now we're actually going to do something totally different. So information theory, it's basically the science of, firstly, reliable, and secondly, efficient information transmission. So this, under information theory, come two headings. One is source coding, and that is possibly better known as compression, data compression. And the second heading is channel coding. And that is possibly better known as error correction. So what we're going to do for the remaining lectures that we have together is we're going to talk about source coding and channel coding. Source coding has absolutely nothing to do with errors. So it has nothing to do with it has nothing to do with calculating probability of error. All it has to do with is assuming that no errors occur in transmission, what's the shortest description of a particular string that you can possibly have. So in fact, we all use source coding daily. So I mean, we all know what zip archives are. That's just source coding. That's compression. We all know what there are Unix tools like gzip. A lot of document standards use source coding without even thinking about it. So, for instance, PDF is compressed. So those are all examples of what's called lossless compression. In other words, you compress something, blow it up, and it's exactly the same thing as you had before. There are lots of examples of lossy compression, which is where you shrink something, blow it back up, and it's an approximation of what it was. So that's seen a lot in, for example, music encoding, like MP3 is lossy compression. JPEG for images, lossy compression. Most of the video standards are lossy because the human eye, the human ear can't detect those kinds of subtle differences. Channel coding. So if I give you the other side of this is channel coding. So if I give you a channel and I say in this channel the probability of error is 10 to the minus 3, and you say, well, that's not good enough, what I really need is 10 to the minus 5, that's where channel coding comes in. So in channel coding, what you do is you have a sequence of bits, and then you add some redundant bits. So those redundant bits can do one of two things. Firstly, they can tell you that you have an error. So in other words, if the redundant bits don't match up with the original bits, they can tell you that you have an error. And what you can do then is you can ask for retransmission. So that's called error detection. They can also, if they're sufficiently sophisticated, those redundant bits can tell you where the error occurred, so you can flip that bit back, and that's error correction. So we're going to look at, in source coding, we're going to look at a very simple scheme called the Huffman code. And in channel coding, we're going to look at two schemes. One's called the Hammond code, and the other one is called a convolutional code, which sounds really complicated, but it's actually kind of easy. So, talk a bit about source coding. So what I'm going to do for the rest of today, I'm going to talk a bit about compact data representation. So source coding is about compact data representation. So, as one example, let's think about a security system. And in this security system, what we're going to do is we're going to take a sample of the state of a door. Every 1/10 of a second, we're going to sample that door, and we're going to report whether it's open or closed. So we're going to say, door open equals 1, and door closed equals 0. So what would we expect from the signal? What we would expect is that for long periods of time, we would have lots and lots and lots of zeros. And then for short periods of time, we would have ones. So this could be minutes to hours. And this could be seconds. And then again, minutes to hours. And so on. So basically what we're doing here is we're keeping a log of the times at which the door is open and the times at which the door is closed. So if we're sampling at a rate of every 1/10 of a second, so 10 bits per second is the rate at which we're collecting data. Then after a minute, we would have 600 bits per minute. After an hour, we would have 36 kilobits. After a day, we would have roughly 900. Basically, roughly a megabyte. Roughly a megabyte per day. So over 365 days, over a year, we'd have approximately 300. These are just approximate anyway, so it doesn't really matter. About 300 megabytes per year. So if you had a huge building with 1,000 doors or something like that, and all of them required monitoring, and you wanted information going back 10 years or something of whenever those doors were open or closed, ballpark, we're talking about 3 terabytes of just a signal like this. So, given that this signal has a lot of structure, can anyone propose a far more compact way to represent that signal? Yes?
Well, we can just say we have this many zeros and then this many ones.
Exactly. So that's an excellent way to compress the signal. So let's say the door is closed for an hour. So that would be, so what you would say is that you would have 36,000 zeros, and then maybe some comma characters separated, and then it's open for 10 seconds. Then you would have 100 ones, and then a comma to separate, and then you would have it's closed for another 2 hours, so that'd be 72,000. So on. So what you have to do to make this a fair comparison, these are bits, so you would have to compare in terms of bits. So what you would have is 10 digits plus a unique comma character. So basically you have 11 letters in this alphabet, and you would have to ensure that the equivalent number of bits, if you were to take this and actually represent it in bits, then it would actually be more compact. But I think it should be obvious that this is a far more compact representation than that. So a natural question is, what is the most compact possible representation?